All right. Now, speaking of which, how important is this? Really important clinically. These are pictures that you've seen over and over again, but a number of things that we can walk you through here. Let's begin. First and foremost, I want you to take a look at the picture in which we find a left ventricular pressure, the green line, and then you're comparing this to the red line, which is the aortic pressure. At that first point where we have just completed diastole at the bottom of the valley, and then you're moving up that curve, what's that called? Isovolumetric contraction, isn't it? Of what? The left ventricle. Good. And the left ventricle is building up pressure, building up pressure, building up pressure. Would you tell me how much blood is in your left ventricle right now? It's the fullest that it can be, right? It's the fullest that it can be. And it's building enough pressure so that it can do what? Open up that aortic valve. Aha! That's my problem. And on a question, they could actually put A, B, C, D, E on this graph and ask you, where is my pathology located for aortic stenosis? It would be at that point where that green line intersects with that aortic pressure, and it's trying to open up, but it can't. So what does the left ventricle have to do? It has to continue building that pressure. How is that represented? You see that shade underneath that curve? That peachish shade? That's a pretty color, isn't it? That peachish shade that you see underneath that curve represents the increased pressure of the left ventricle lifting up weights so that it can overcome the afterload of the stenotic aortic valve. Is that clear? How are you going to represent this? Well, here's S1 and there's S2. You see them? Now, S1 is going to represent what? Closure of the mitral valve. Remember, S1 is never opening. Actually, no heart sound is created by opening. Is that clear? We've talked about that a few times now. So, where is my mitral valve closing? At the bottom of that valley. At the end of your diastole, right before you begin isovolumetric contraction. And so therefore, when that mitral valve closes, you're building up pressure, crescendo, crescendo, decrescendo, crescendo, boom, aortic valve opens, decrescendo. It's a diamond in the rough. It's a diamond between S1 and S2, a crescendo, decrescendo type of murmur. Welcome to aortic stenosis. How's the patient feeling? Tell me. Tired, fatigue. Not you guys. You're feeling motivated right now. You want to learn more. You're thirsty for knowledge. Let's continue. So you have a crescendo, decrescendo type of murmur. Next, let's take a look at the pressure volume loop. In the pressure volume loop, well, we'll take a look at two here. One is going to be the blue curve. You see that solid blue curve? And that is going to be normal. Listen to what I'm saying. That solid blue curve represents normal pressure volume loop. Okay? Now, with that, you begin at a point where it's a diastole. The x-axis represents volume, and the y-axis represents pressure. You see that? X-axis volume, y line is going to be pressure. And so now you begin increasing volume. You increase your volume, increase your volume, increase your volume. Boom. What do you do now? You close your mitral valve. You close your mitral valve and you move up the y-axis, which means what? You increase the pressure. You see that? So now this is the pressure volume loop that you're oh so comfortable with. And that blue line represents normal. And you move up that pressure, and eventually you'll open up that aortic valve. When you open up that aortic valve, you go directly into what's known as your rapid ejection. Which way are you following the pressure volume loop? You're following it counterclockwise. Not clockwise, counterclockwise. That must be understood. It's the only way that you'll get this right. I want you to compare that point where the aortic valve should open and compare that to the dash line. That dash line continues to increase pressure. Why? Because the aortic valve doesn't want to open. Is that clear? So anytime that you find a curve in which it is much more increased in pressure compared to normal, then that to you automatically should mean what? Aortic stenosis. And now, let me ask you something. If that aortic valve doesn't want to open, and by the time you finally do, then would you tell me what stroke volume equals? Close your eyes. Stroke volume equals, when is your heart or ventricle the fullest? At the end of diastole or end of systole? Take your time. You got this? Good. At the end of diastole is when the left ventricle is the fullest, isn't it? From this, you subtract your end systolic volume. What is that going to give you? Stroke volume. Is that clear? So how does that represent? On the pressure volume loop, the area between the curve, or area underneath the curve, represents the stroke volume. So now in aortic stenosis, how do you open up that aortic valve? Systole. And so you open up that aortic valve. And once you do so, the blood is being ejected. How much blood is left at the end of systole? It's the least that the left ventricle contains. In aortic stenosis, when that aortic valve doesn't want to open, then at the end of systole, how much more blood do you have left in your left ventricle? A little bit more. Do you see that dash curve? And so when you follow it with counterclockwise, you'll notice that end systolic volume is actually increased. Is that clear? When your end systolic volume is increased, and in the equation where stroke volume is equal to end diastolic volume minus your end systolic volume, with an increase in end systolic volume, what have you done to stroke volume? You've decreased it. These are the type of questions that you're going to get integrated with pathology and physiology. If you weaken these particular areas, I would highly recommend you go back and take a look at your physio so that you're perfectly clear with every single one of these clinical points. We must continue. Aortic stenosis, pathophys. As the valve area decreases, left ventricle must work harder. What is the left ventricle going to do? Increase thickness. It's going to increase the demand for oxygen. It could or could not be met. If it's not met, then we have issues with what's called as angina. In response to the increased workload, what kind of effect is the left ventricle undergoing? Hypertrophy. What kind of hypertrophy is this? It's the fact that the sarcomeres are going to duplicate in parallel, and parallel. It's called concentric hypertrophy. If you take a look at these hearts, it shows exactly that. Let me walk you through this. You see the normal heart? You see where it says LV, left ventricle? That's the normal left ventricle. But Dr. Raj, it looks thickened. Yes, it's supposed to be normally. The left ventricle has a heck of a lot of responsibility of supplying blood to the entire body. And so therefore, it has to have increased pressure. 120/80. You know that already. Now I want you to compare the thickness of the left ventricle of normal versus what you're seeing here with concentric hypertrophy. Concentric hypertrophy, you have increased thickness. What caused that? Increased pressure. In this case, by whom? Aortic stenosis. The left ventricle was lifting weights and it underwent hypertrophy. You tell me once again, what happens to stroke volume here with aortic stenosis? It decreases. Why? Because of increased end systolic volume. Why? Because at the end of systole, there's more blood left in left ventricle because of that stenotic aortic valve. Is that clear? Make sure it is before you move on, or otherwise, you want to make sure you solidify that point forevermore before taking a look at any other issues. Now, in terms of concentric hypertrophy, that's exactly what we just talked about, that bigger left ventricle.